Today's video is on topic 4.1, 4.3, and topic 4.2. In topic 4.1 and 4.3, we're talking about interpreting the meaning of a derivative in context and looking at those contexts that are other than motion problems. So the best way to do that would be to actually look at released free response questions. Now, when we're interpreting the derivative in context, the way we interpret the derivative at a certain value when we're given or have to find the rate of change, the derivative. It's very, very simple in terms of there are 5 key things that we need to write as we write this interpretation. This process is very similar to how you write a thesis statement. It needs to have X, Y, Z in order to be a good thesis statement. These are the 5 things we need in order to have a solid interpretation of the derivative. We have to make sure we're mentioning the context in which the problem is rooted. After which we're going to say that function is either increasing or decreasing. Of course, comes from the sign of our derivative value at that point. Then we must say at a rate of. We must make the phrase at a rate of part of our interpretation, because really, finding the derivative, we're finding a rate of change. Next, we'll write the numerical value with units, making sure units are involved. And then finally, we will say at the certain time units. It may not always be time, it may be something else. But usually it's time, including the units. And there it is. So to try this process out, we're going to start off with using question 2001, question number 2. Take a moment and read this. By pausing the video, I'll resume in 3, 2, 1. Identifying the key pieces of information in part A, we need to use our table to approximate W prime of 12 and showing our computations and using units appropriately. In part C, we have a new function that's been introduced, P of t, 20 plus 10 times t e to the negative t over 3, that's going to model the temperature of the water. And in this case, we want to find P prime of 12, and then there is where we're going to go ahead and explain the meaning of this answer in terms of the context of the temperature of the water. If we look at the scoring guide for this, we will get 2 points for part A and 2 points for part C. From A, we need the difference quotient and our answer with units. In part C, we get an answer for P prime of 12, and then 1 point for our full interpretation. So, can we approximate the instantaneous rate of change of W at 12? The average rate of change, of course. So W of 15 minus W of 9 over 15 minus 9. Evaluating gives us 21 minus 24 over 15 minus 9 degrees Celsius per day. Remember, we don't need to simplify as this is a free response question. We've written our difference quotient, including our answer with units. Okay, for part C, we now need to find P prime of 12. And as much fun as it would be to take the derivative by hand, we are given the option of using the calculator in this particular problem. So we're going to go ahead and do that. So we're going to take the derivative of function P at time is equal to 12 using our calculator. Pause the video for a minute and check in with your neighbor to make sure you both know how to find the derivative using the calculator. Unpause the video then. I'll reveal the answer in 3, 2, 1. And we find P prime of 12 to be negative 0.549 degrees Celsius per day. All right, now comes the last point for interpretation. Using our stem from above, take a moment and see whether or not you can get the interpretation. Following the mode, I'll reveal the answer in 3, 2, 1. The temperature of water in the pond is decreasing at a rate of 0.549 degrees Celsius per day, and time equals 12 days. How'd you do? Did you get all 5? Hopefully so. All right, now that we have one under our belt, why don't you go ahead and try question number 3 from the 2007 exam, Form B, where it discusses the wind chill, and we're trying to find W prime of 12 and then interpret and explain the meaning in terms of the wind chill. Pause the video, give it a try. I'll reveal the answer in 3, 2, 1. How'd you do? Did you get all the pieces? Hopefully so. Well done. On the back of these notes, you will see we have additionally 2 more problems, one from 2010 and one from 2017. This is the infamous banana problem. This one caused students lots of issues. We're going to save part B and part C for in class when we meet again. If you'd like to go ahead one more time and try part B in 2017, 17. Regarding the bananas, we're in part B, you're trying to find w prime of 7 and explain the meaning of w prime of 7 from given the function f of t up above. Pause the video and give it a try. I'll reveal the answer in 3, 2, 1. F prime of 7 is negative 8.120 pounds of bananas per hour. Did you catch the units? F of t is measured in pounds per hour, and t is measured in hours. So interesting, the units here may be causing us a bit of an issue as we take a look and making sure that our units are correct as we're writing them in the problem. Hopefully you got that correct in using the calculator. Very well done interpreting derivatives in context. We have to have all 5 pieces in order to get the full point. Make sure we have this for when our upcoming concept check, as well as on our assessment. Moving on to topic 4.2, straight line motion connecting position, velocity, and acceleration. So this type of question is very common on the AP exam, talking about particles and bugs. For our purposes, the problem will usually look like something from unit number 9, which we'll be covering back down in quarter number 3, but all of that will build on this knowledge we have here in topic 4.2, just basic position, velocity, and acceleration. Now, in order to answer these problems correctly, we need to decode the questions and the language of the expression into what that means in terms of a math translation. So what I've done for us here is listed some common motion expressions in the left-hand column and provided us with the math translation, what we need to actually do in the right. Take a moment or two and peruse over this list. Pause the video to do so, and we'll talk about a few highlights. Continuing in 3, 2, 1. All right, so to start with, you should note that initial position is usually denoted when as s of 0 or x of 0, and then from there we have particles position, instantaneous velocity, and acceleration. Velocity being the derivative of position, and acceleration being the derivative of velocity or the second derivative of position. Now, key phrases that show up are when is the particle at rest, when is the particle moving right, when is the particle moving left, when is the particle changing direction. We should note that when a particle is at rest, the velocity is 0. What particle is moving right when our velocity is greater than 0, it's moving left when it's less than 0, and it changes direction when the velocity changes signs from either positive to negative or negative to positive. Now again, in this entire scenario, a particle or bug, my drawing, is stuck on a one-dimensional line. We're moving left or right, left or right, left or right. We're kind of stuck on the x-axis, if you will, moving back and forth. As we get farther on, specifically in unit 9, parametric and polar, we're going to see that this bug is going to have a little bit more freedom, and he's going to be able to move left and right, but also up and down, giving that two-dimensional motion, which adds a little bit more complexity to it, which is kind of the style of question we'll have on our AP exam. But for now, the bug is just stuck on a line, moving back and forth, so we can look at the velocity as it's going through. A couple other key phrases that we should reckon is the velocity of a particle is increasing or decreasing depending on what the acceleration looks like. For speed, the speed of a particle is the absolute value of velocity, but we're also going to note that we could write this as the square root of velocity squared. So an interpretation of the speed in order to get the absolute value. You can also write it by definition as the square root of velocity squared. This looks a little odd, but just trust me on this one. We want to make sure we have this other interpretation of the velocity in our head, because when we get to two-dimensional motion, we're going to define it with this second portion. Because think about it. As of right now, the bug is just moving side to side, left to right. He's stuck moving left to right, so his velocity is only in one dimension. So his speed is only affected by this one-dimensional motion. However, if I told you that the bug is now able to move up and down at the same time, its speed is going to be affected not just by left to right, but also by up and down motion, which would be a separate instance. Those physics people know what I'm talking about. So we want to make sure our calculation will get a little bit more difficult, not necessarily too crazy. So we want to make sure we remember speed is the absolute value of velocity, or the square root of velocity squared. Now, in terms of finding the speed of a particle, whether it's increasing or decreasing, we should remember that this is all dependent upon the signs of velocity and acceleration. If they're the same sign or whether they are different signs, that tells us whether the particle or the bug is increasing or decreasing in speed. It's increasing when the velocity and acceleration have the same sign and decreasing when it has opposite signs. Okay, so over that quick overview, we have some problems to take a look at involving speed. Please note that the very last few pages is going to be our practice for the day, which is a Big 10 activity, courtesy of Brian Passwater. There are 10 problems, and all 10 problems, the answers are either 0 through 9. That's it, and only the number will only be used once. So if you get an answer of 27, you messed up. So there's 10 problems for you to go ahead and give it a try. Making sure you're checking off the answers as you go through. That'll be our practice after we quickly talk about some examples. Now, we have to make sure we're justifying our answers, not just by using sign charts, but by actually using good mathematical terminology. By that, I mean our reasoning and our translations. The stuff we have listed here in the right-hand column is perfect for what we actually want to say. We want to go ahead and use this specific language as we answer our questions if they ask us to go ahead and justify. So here is our first particular problem. We have v of t, the graph listed from 0 to 13 of some type of bug. See whether or not you can complete problems numbers 1 through 4. And in 4, make sure we're giving a good justification for our answer, as well as in number 3. I'll reveal the answer in 3, 2, 1. How do we do? In part 3, notice we're asking when the bug turns around. We know this is that t is equal to 9, and our justification is that the velocity changes from positive to negative. Could have also been from negative to positive. That's the way the graph looked. Got to make sure we use the phrase. In part 4, we want negative acceleration. Negative acceleration means we want where the velocity is less than 0. This occurs when the graph of v of t is decreasing, and that's between 7 and 10. All right, one final question here. How many times is the speed of the bug equal to 2? We want to know when the speed equals 2. That means when the velocity is 2 and negative 2. And looking at our graph, that looks like they occurs 2 times each, means for a total of 4 times. Okay. Let's take a look at this problem. Now, in this particular scenario, I gave us the graph to look at, but ideally what would happen is you would not be given this graph and you would have to produce this on your own on your calculator. However, I've gone ahead and done that for us. This interval from 0 to 12, you could graph it. Notice I've zoomed in from about 0 to 3 because most of the questions are asking us between the intervals like 1 to 2 or 0 to 2. So I made my graph from 0 to about 3 to give us a little bit more room, but you would not be given this graph. You would want to make this on your calculator using the functions listed there. So we have these 4 questions for us to answer. When is the bug slowing down or is it slowing down or speeding up at time equals 0.7? Find the values of t in the interval where the bug is at rest. On the open interval, when is the bug moving right? And lastly, when is the acceleration of the bug at velocity when the velocity is equal to -2? Interesting for us. Some of these values, you're actually going to have to find the intersection on our calculator. So if I want to find the bug is at rest, looking for where the velocity is equal to 0, and we know when we're moving right, we mean the velocity is greater than 0. Along those lines. So for the velocity equal to 0, we can either use the zeros option on our calculator, or we could graph y equals 0 and then use the intersect feature on our calculator to go ahead and find these 3 very visible intersection points. We would have to go ahead and find those using the calculator feature. And then, of course, use those intervals to try to help us when the bug is moving right along the way. Take a moment and see if we could figure these out. Please remember, you could also store these answers. So the first one must be 0, but of the second 2 intersection points, remember, we can store these values in our calculator as A and B if we need to use them later on in a particular problem. I don't think we're going to exactly need those here. Maybe in part D, when we find a new value, it may be helpful for us to go ahead and store that as another value, but storing is something we can do make sure we want to remember that. Okay, give this one a try, and I'll reveal the answer in 3, 2, 1. All right, so how'd we do? Take a moment and check your answer, and maybe check in with a table partner to see how they're doing, whether they got the same answer, whether they need some additional assistance with a calculator. I would note the part 4 here, where we had to find where the acceleration of the bug when the velocity equaled -1. Here we needed to go ahead and do an intersect on our calculator. Y1, we should already have our function v of t stored. For y2, we'd write -1. And then using the intersect feature, we can see that that occurs at time approximately 1.83. We can store that at c. And then from there, going back to the home screen, we can just simply evaluate v prime of t at c and figure out that value as -28.874. Again, check in with the table mate, make sure they got this one correct and they know all the bells and whistles of our graphing calculator that we had discussed how to find the derivative of earlier before moving on to the next problem. Now for part C, we introduce a couple different question types to the mix involving whether the particle is moving towards or away from the origin, as well as whether or not the particles are moving towards or away from each other. I will note that we're going to go over problem C in class next time we meet. However, I think we should be okay with these if I give us the hint that we're actually going to need the position and the velocity of both of these in order to figure out where they are, and the velocity would tell us whether they're moving left or right in each of these particular problems. And if you take a moment and read example D, what does that scream to you? Yes, IVT. It's never going away. We want to make sure we try that one out as we're going through. We're going to go over example C together when we meet. With that being said, why don't you use the rest of the time to go ahead and try this Brian Passwater, these 10 problems. Go ahead and work with your table to see how many of these we can get. We'll continue working on this next time I see you. Make sure you are working on the My AP questions as well as the progress checks that are listed there. We want to make sure we're getting our additional practice at the AP level. Those My AP questions are wonderful to kind of give you a different look and challenge you in a different way that these classwork can. Thanks.